Welcome to Heat and Materials Lecture 7. In the previous lecture I looked at the incorporation of heat generation into steady state problems in 1D, and I particularly looked at a one-dimensional cylindrical case for the temperature distribution within a cylinder of high-level vitrified nuclear waste. I now want to move on to a very different sort of problem, in that I'm going to look at generalizing the heat conduction equation to 3 dimensions, and then to look at 2-dimensional problems involving Fourier series. Now, Fourier series are a very useful technique for solving a number of problems. In this case, I'll be dealing with a steady state problem with no internal heat generation, and I will look at the specific example at the end of the lecture of a uniform elevated temperature along one edge and some of the limitations of that specific solution. Now, obviously, if we're dealing with 2D, we can technically deal with either 2 spatial dimensions or 1 spatial dimension and time. And if we can separate the 2 dimensions so we can treat them independently, then a Fourier series may be beneficial in obtaining a solution. Previously, we have seen heat conduction equation in 1D, where I had this time-dependent term, the term that depends on x, and the heat generation term. I now want to generalize to 3 spatial dimensions, and I do this by including 2 terms that are equivalent to the partial d by partial dx, k partial dt by dx, but written in terms of y and z. So I'm just writing down equivalent terms for the other 2 Cartesian directions. And if, as in previous examples, k is not a function of position, then we can simplify these 3 terms slightly by bringing k out of the differentials, so that we end up with this overall result shown here, involving a time dependence term, 3 position dependent terms, and a heat generation term. Now, if no heat is generated internally, then Q dot will go to 0. We've already said that we'll consider the case of k being independent of position, and in those circumstances, if Q dot is 0, obviously that term has disappeared. I can now cross multiply by rho Cp, and that will give me k over rho Cp, which we also know as alpha, or the thermal diffusivity. If this equation is time independent, then clearly the left hand side, the time dependent term, will be 0, and we end up with this relatively simple expression shown at the bottom of the slide. This equation is actually well known in other areas and is known as the Laplace equation. Something that is equivalent from a mathematical perspective crops up in electrostatics, for example. And you might be familiar with this particular notation, which is effectively an abbreviated notation for the same equation. I won't be using it in the rest of this course. It's simply there to flag up there is this alternative contracted notation. If you're familiar with it, the advantage of the contracted notation is it does not actually depend on coordinate system. You can find different expressions for this term del squared, for whether you're dealing with Cartesians as here, or whether we're dealing with some other geometries such as spherical polars or cylindrical polars. However, throughout the rest of this course, I will use the notation shown in the equation in blue. So that's the basic equation that we would try and solve in 3D. And what I want to do now is to start to consider a problem for a steady state temperature distribution, but I'm going to actually do this in 2D. So thinking effectively of a thin plate that's a uniform temperature through its thickness, and that essentially has some imposed temperature distribution along one edge, and all the other edges are at some initial temperature which we will call T0. We'll consider the case of no internal heat generation and ask the question of what does the temperature distribution look like inside the plate, and also whether we can calculate the heat flows and heat fluxes, which we would expect to be able to do once we have a temperature distribution by simply applying Fourier's law. At this stage, I'm not going to make any assumptions about my imposed temperature distribution along one edge. This could be any function that you like. We now, for simplicity, subtract the constant temperature T0 at all points. This means that along the bottom edge the temperature becomes T equals 0, and the two sides temperature is also T equals 0, and along the top edge we now have a new function T2, which is simply equal to T1 minus T0. This simplifies the overall solution, and we simply have to remember to add in T0 at the end of our solution process. The equation that we're solving is partial d2t by partial dx squared plus partial d2t by partial dy squared equals 0, because we're dealing with a steady state two-dimensional problem with no internal heat generation, and our boundary conditions are formally that t equals 0 if x equals 0, i.e. along this edge, t equals 0 if x equals L, i.e. along this edge, or t equals 0 if y equals 0, along the bottom edge, and then along the top t equals t2 of x h if y equals h.